All right, let's look at a real life example of one of these directional fields for this simple circuit shown below. So this figure gives a circuit that would be driven by an electromotive force, usually like a battery or generator. And what it's going to do is produce a voltage, which they're calling E on this one. So here's E in our equation. Uh, and and that would be like whatever's hooked up to this, like a battery. You're going to get a current, which is I in this equation, and that's a current's measured in something called amps or amperes. The circuit also contains a resistor with a resistance of R, which is measured in ohms. So R is here in our equation. Here's an example. Here's like what they use to draw a resistor in a current. Um, and an inductor, which they use L for. Here's our inductor and our current measured in something called Henry's. Ohm's law, which you don't need to know, but it gives a voltage drop due to a resistor as R times I. So that's why we see R times I in here. The voltage drop due to the inductor is the inductance times the, and you can see here we got a rate of change. That's our rate of change of our current compared to time. So that's what this is. And there's also another law called Kirchhoff's law that says the sum of these then equals the voltage drop, and our voltage here is E. So this is a differential equation because you can see here in this equation we have a rate of change here. The rate of change of the current is given. So that's what makes this a differential equation. So what we're going to do is use this to try to answer some questions now. So it says, suppose in this circuit that the resistance is 12 amps. So we're going to plug 12 in for R. The voltage is 60. Voltage was E in this one. And the inductance is 4 Henry. So in this equation, 4 is represented by this variable L. So if we plug all those in now, that gives us this equation here for change in our current over time plus our resistance here was 12. Our current is still there equals our voltage, which is 60. So simplifying this a little bit, I'm gonna since all these have a 4 here, I'm gonna divide each of these by 4 here. So now we got this differential that says our rate of change of our current plus 12 divided by 4 is 3 times our current equals 60 divided by 4 is 15. And then to get our current or our rate of change here by itself, I'm going to minus that over. So then we get 15 minus 3i. So there is a equation now, a differential equation we can use here to do part A, where they want us to draw our directional field. Rather than draw it out by hand, let's use technology again. So let's enter this on Desmos, but instead of I and T, if we enter this on Desmos, then I is like our Y, X is like our T, so this would get entered as this, and I was our Y here, so this would be minus 3Y. So let's go to Desmos and enter this in and see what this directional field ends up looking like. Again, that link is in Schoology. So let's go here, let's type this one in, 15 minus 3y, and we do that. Here is our directional field for this one. So that's a picture of what this looks like. All right, so next question now. Identify what you can say about the limiting value of this current. So what they're talking about with a limiting value is what would we get if we did for this equation the limit as this goes to infinity for this function here, 15 minus 3i. So as this current here goes to infinity, what are we going to get for this? So, or sorry, not I. As our time goes to infinity, that's what I meant to. As our time goes to infinity, what is this going to approach here for this differential? So what we're looking at is on the picture here, as time goes to infinity, what is this going to go to? Well, if you look here, no matter where we start, if we start here, it's going to go like this. If our time starts down here, looks like we're coming up. What does all these approach no matter where you go? It looks like it approaches, it's going to approach 5. So no matter where we start, these directional fields are pushing us towards 5. And so our limiting value, since it's 5, what that tells us is that would be our equilibrium solution. So when our equilibrium solution was when the current equals 5. So that would be what we got for part C. All right, last part. If the switch is closed when t equals 0, so the current starts at the point 0, 0, use the directional field to sketch that one out. So let's go back to our picture here. Erase these. So let's start at 0, 0, which is right here. So following the slope fields here, looks like it's going to do something like this. So that would be what the current would grow until it reaches 5 amps, and then it stays over like that.